Hi guys, Buildzoid here, and today we're going to be disassembling this here Gainward GTX 580 Phantom 3 GB GPU. You might be wondering why we're disassembling a GTX 580, and that's very simple. I think this card's a bit interesting. If I didn't think it was a bit interesting, we wouldn't be here, would we? So anyway, I did get this on eBay, as you would, because they don't make these new anymore. Um, and yeah, I mean, the first thing that's kind of interesting about this card is obviously the heatsink setup, because where are the fans? Well, that's very simple. They're inside. And more concerningly, they're in a pull configuration, and they aren't shrouded. And the reason I say that's kind of concerning is because fans are not really that good at pulling air. They're a lot better at pushing air through restrictions. And the fact that these don't have a shroud just means like there's like, like the fan is just gonna, I think it's with the blade design, it's probably not gonna pull air in from the side, but it's just like, I guess it's just gonna like spray air in all directions, and the idea is some of it will make it through the fin stack, and that'll provide some cooling, I guess, because yeah, this really is this is a unique way of designing a heatsink, and they unfortunately stopped doing it, I think, after the 700 series. Actually, no, I think there might be some 900 series cards that still use this style of heatsink from Gainward. Yeah, I mean, I can't imagine that it's any worse than the reference blower for a GTX 580, but I have my doubts about this being particularly efficient. And so one of the things I do want to try is just like pointing a, like a case fan directly at it, which to be fair, if you do that with most GPUs, it'll give you drastically better temperatures. Because the fans that a GPU comes with, like you can see, these are actually like pretty, like as far as actual like depth dimensions go, these are actually pretty standard for a GPU heatsink. They're just in a weird location. And yeah, so like GPU heatsink fans are generally not very good. And so case fans will generally do a much better job of actually shoving air through a fin stack. And in this case, like these are also trying to pull the air through the fin stack. So yeah, I do wonder, like, 100% fan speed on these versus just like pointing a case fan at the front of this. How kind of like what kind of temperatures that delivers. So that's one thing, is the heatsink is a bit special. The other thing that's a bit special about this card is it's obviously a 3 GB GTX 580, though you will notice that it's not like we have any extra memory chips on the back. And the reason for this is that at the time that the GTX 580 was being produced, they already had the higher density memory chips that the 3 GB cards require. It's just NVIDIA, being NVIDIA, decided that the standard configuration should be 1.5 gigs instead of 3 gigs. So as far as I know, the 1.5 gig cards generally clock memory better. So from a overclocking perspective, the 3 gig configuration isn't really much, like, it's not necessarily a good thing. I mean, it does mean that, like, you should be able to run Firestrike Ultra without the GPU having to constantly pull data from the system memory. But on the flip side, Firestrike Ultra on a GTX 580 is going to still run at like 3 FPS. So that's not really a relevant application, is it? Anyway, so yeah, the 3 gigs of memory, it's, a bit special. But the other reason, and sort of the main reason I went specifically for this card and not one of the other cards, because I've wanted one of these Gainward cards with this heatsink for a while, just because it's an interesting heatsink design. So I kind of want at least one sample of this style of heatsink. But the reason I went specifically for the GTX 580 is because the way the power delivery on this card is laid out is a little bit unique. Like, not something you really see on most GPUs. It's not anything like super special in terms of like, oh, this is going to deliver amazing extreme overclocking capabilities or something. But it is an approach that makes sense. Like the reasoning behind why the VRM is laid out the way it is makes sense, and I thought it would be interesting to take a look at a card that actually does this, because you don't usually see the VRM layout that we're going to see once we take this apart. But before we take this apart, I am wondering if these polymers over here are for vCore or for memory. Because obviously we've got the memory chips around here, but I'm pretty sure these are for vCore. And the reason I say these are probably for vCore is because like GTX 560 Ti's actually And I think 560s and maybe also 460s do this thing where you just have like these polymers that are like for vCore, but they look like they're sort of stuffed into the memory power plane. Because if you actually, I can't tell if you can. Well, anyway, so here we have a two-phase memory VRM. These are the inductors for it. And basically this entire, well, most of this area back here is actually memory power plane, right? So like this over here is memory power plane, this over here, memory power plane, that like basically, yeah, like the big, like the main polygon that we have on the back of the card is basically memory power delivery. So anyway, and I'm wondering if these are connected to the memory power plane or if they're like tied through some vias into the vCore power plane that's inside the PCB. Because yeah, on the other side of the card, we're probably just going to have data lines. Anyway, so we've got the multimeter out. This is a pretty easy check. We're going to take one probe onto the inductor legs, and then actually we're going to take the other probe because this one's big and blunt. And I'm just going to get this. Oh, so it is memory. Cool. Yeah, that's connected to the memory power delivery. Is that all of them? Right. Not doing a good job. Yeah, that definitely looks like it's all memory power delivery. Now, one thing that's kind of funky with GTX 580s is that they have a very low core resistance. So like the memory resistance, right, if we just measure against one of the output filtering capacitors for the memory, 45 ohms. This will vary by like what memory chips the GPU uses and that kind of thing. So for this 3 gig card, 45 ohms is the resistance of the memory. But the core, we're probably going to see like, oh, it's 1 ohm. That's actually quite high for a GTX 580. I've seen a lot of 580s that'll measure like half a ohm. So that is, yeah, that is surprisingly high. I was really expecting to see something lower. So that's kind of nice, because obviously when you have a card where the core, even in working condition, looks almost like a short circuit, makes troubleshooting potentially a bit more annoying. Another thing that I find kind of funky about this card, though it doesn't really affect anything, is this shunt resistor over here. So there's basically a great big power trace all the way from the PCIe slot to over here, which I just find kind of interesting because most GPU manufacturers would take this shunt resistor and put it right there. And Gainward put it up here. It doesn't affect anything, but yeah, it's just kind of interesting to, because normally you expect to see that shunt just right by the PCIe slot. Here, it's all the way up here. Then over here, also, this is, I think this is from the factory, I'm not sure. You might notice there's like a yellow goop over this chip over here. This should be a Texas Instruments INA 219, which is the current, like the shunt monitoring chip. So that just monitors the voltage drop across the shunt and then reports that to the GPU so that the GPU knows how much power it's pulling. What's interesting is, yeah, we have like these glue blobs around, like on some of the components here. I think it's glue. It might be epoxy. Well, epoxy, glue, same thing, kind of, right? Anyway, yeah, so kind of interesting. I guess it's to prevent these from getting knocked off, because I think they're kind of the tallest. Actually, no, they're shorter than these capacitors, so I'm really not sure why they're doing that. These aren't that tall, but I guess maybe they had, like, issues with people scraping those components off the board, because, yeah, I can't imagine why else you'd have this, like, yellow gunk over them. Anyway, let's get to the actual disassembly. As far as I can tell, I think the heatsink is actually going to pop right off with just the bracket. And I'm basing that off of the fact that, like, yeah, we have these, like, plastic supports here, but these don't actually seem to connect to anything. They seem to really be, like, yeah, as far as I can tell, I don't know if it shows up on camera, like, that's just free floating, as far as I can tell. Yeah, and actually here you can, like, that doesn't actually connect to anything. That's just kind of there, right? Same here. So, yeah, as far as I can tell, this is actually 2 separate pieces. We have, like, a base plate, and then the heatsink just sort of attaches over here. And the base plate has a lot of screws, and the heatsink has 4. So, let's see if I'm right about that. Also, I guess we could take off the shroud separately if we wanted to. I'm not sure why you'd want to. It's not like it would give you access to anything, right? There's some other cards where you would potentially want to pull the shroud to, like, clean the heatsink out, but this is not one of them. We do have a leaf spring for the core, like for making good contact pressure with the core. I hate leaf springs. They make disassembly. Actually, this one's not too bad. But like some of the leaf springs out there are incredibly heavy and they make reassembly an absolute nightmare. So yeah. Oh, and these are even like they even have the whole like it's not round so that the leaf spring can move more freely as you like screw it down. So this one doesn't seem that heavy, so I don't think it'll pop right up. One of the main thing I dislike about these is when you're like tightening them down is that obviously it wants to like rock the GPU on the heatsink. And with a GTX 580, that's not really too much of a concern because these things have a heat spreader to make them run extra hot. Because yeah, there's thermal paste under that heat spreader, not solder. So now we're gonna find out if I was wrong about this being. Wow, this really doesn't want to. Wait, are these also for the? These might be for the heatsink assembly. I mean, for the. Like, I like technically there's a PCB heatsink, right? So that doesn't really make sense. But I think these might be for the core heatsink. Still not letting go. But like, the shroud isn't screwed into anything, so like. I would have figured that like. Huh. Oh, I guess this is one of the. This was actually kind of common on Fermi GPUs, is that you'd bolt the heatsink to the base plate, which is really weird why they're still using. Well, I guess no, it still makes sense because it'll still push the core into the heatsink a bit more than just like not using the leaf spring, but interesting. So I imagine the actual heatsink is bolted at the like base to the base plate. So yeah, kind of a weird assembly. Or weird. Yeah, kind of weird compared to a lot of like later cards. Because a lot of later cards will just have the heatsink separate from the like memory and VRM cooling, and I prefer that because it means that like if you like screw up on the thermal pad sizing, it doesn't like mess with the core temperatures because they're independent heatsink assemblies. But this isn't. Hopefully the thermal pads aren't in too bad condition. I don't really feel like replacing them. Oh, also, I guess we do have access to the voltage controller directly from the back, and this is a... Ooh, it's an ADP 4100. I don't think that's actually a good thing, but this is like a controller that you see on a lot of Gigabyte cards, and not many other places. So... Yeah. Well... This really doesn't want to come apart. Oh, I forgot a screw up here. Actually, since I forgot a screw up here, is there anything in the I/O bracket? No. Man, I don't like how the, like, now it's like... Yeah, I'm gonna take a little thermal paste spreader and try wedge that. Well, nope, this one's too soft. The thing is, I don't really want to bend the PCB, but there's like not anything to... Dude, this thing is... There's no memory chips down here, right? I'm not... Okay, this isn't gonna work. Man, am I really not? I mean, I really can't see anything that I'd have to, like, take apart, so... This is too thin. I didn't think I'd need a pry tool for this. Yeah, because, like, if I pull on the, like, that's just, like, that doesn't work. It's just, like, it's just the heat pipes getting, like, bent. Oh, right, because the plastic... Okay, you know what? We're gonna pop the shroud off, because it's, like, under this lip here. Man, this is way more disassembly than I thought it would... Like, way more complicated to take apart than I thought it would be. These are long. Oh, right, because they're screwing them into the fin stack. I don't imagine there's inserts in there of any kind. Though, these are, like, machine thread screws, so... Okay, now the... Yeah. Oh, there's dust under it. That doesn't... Yeah, that doesn't achieve anything either. Though, it does prove my point about, like, it's just kind of floating on top of everything. Man. Oh. Oh, it's caught on the cables. Oh, there we go. Something fell out. Oh, that's how they're holding it in place. They have, like, a threaded rod that goes all the way through. That's cool. I've not seen that before. Like, a lot of manufacturers will just dig the... Like, bolt the shroud directly into the fin stack. Okay, I guess I should have maybe even, like, taken off the back plate. I mean, the I/O plate. This thing is way more annoying to take apart than I thought it would be. I bet it's still just a matter of the thermal pads being really sticky. Okay, there's no other screws back there. Okay, that came off. It's a bit dusty. Not too bad, though. I guess that's one of the upsides to the, like, pull-through design, is that it doesn't pick up as much dust. Wait, so I was right. This is separate. Oh, right, because giant... Oh, because, yeah, the lip was holding it in. That's why I didn't want to let go. Yeah, so I was right. This is completely separate. And here we see the card. It looks like some of our inductors are a bit rusty. They faced the fan connectors inwards. You can see the notch. So, like, if you... Oh, and I managed to cut myself, but... Yeah, you see the notches inwards. So, if you're trying to pull this apart and you're thinking, like, oh, I'm just going to wedge a screwdriver to pop the fan headers. Yeah, that's not going to work. So, this really is not designed for disassembly. You can obviously still, like, grab the edges of these, right? With, like, tweezers or something, but yeah, you can't just wedge a screwdriver in. Wait, so now this lets go a lot easier. That is... Oh, because I guess the shroud was pinning absolutely everything under it down. Hop, there we go. Finally. Man, that was way more difficult than I thought it would be. Anyway, here we can see the PCB. And we have unpopulated capacitor pads. So you can probably guess what I'm going to be doing about those right over here. The thermal pads do look good. I am not going to pull them off because I don't want to have to replace them. But yeah, here you can see what I meant by the VRM layout on this being a bit unique. Because basically, like, this is a pretty generic 6-phase V-Core VRM where you have 2 low-side MOSFETs and 1 high-side MOSFET for each phase. But what's different is that most cards that would go with this, like, 2 low-side, 1 high-side MOSFET setup, they'd put them basically right on top of each other, right? So this takes up the, like, enough space that you could probably fit 2 more low-side MOSFETs, or 1 more low-side MOSFET and 1 more high-side MOSFET in each of these phases. But Gainward hasn't done that here. Actually, I think this is probably a palette design. But yeah, so they haven't done that here. Also, we have like chip input filtering inductors, which is an interesting choice. I mean, it is very low profile, so that gives them, like, this is quite the VRM heatsink, right? So that's kind of nice. But yeah, the idea behind this is just it really spreads out the heat generation from the MOSFETs, so it reduces the thermal density, right? Because the thing is, with a lot of MOSFETs and power stages, you will see that they have like a really high nominal current rating. You know, so like, actually, we might just look these up. What are these? These are 4935s, so these are on semiconductor. I think this is exactly the same low-side MOSFET that you would find on an actual like GTX 580 reference card. Yeah, so I did remember correctly. Let me just quickly check that I read the part number right. It is 4935N. Okay, so I did find the right thing. So yeah, here's the data sheet for these MOSFETs, right? And you'll see here that like the maximum drain current is like 93 amps, which is insane. And then you look at the card and it's like, oops. You look at the card and it's like, we've got 2 of these 93 amp MOSFETs in each of these phases. Why would you need 2 93 amp MOSFETs in each of the phases, right? There's 6 phases, so that's like 93 times 12, that's like, you know, that's like over 1,000 amps. And the reason is that 93 amp rating is only true if you can keep the MOSFET very, very cool. And obviously, the closer the MOSFETs are together, well, the more difficult that's going to be to do. So if we go back to the data sheet, you'll notice that like like absolute maximum power dissipation for one of these MOSFETs, which is with a case temperature of 25 degrees Celsius. So that's the, like, you somehow keep the MOSFET at 25 degrees Celsius no matter what. The MOSFET can dissipate 48 watts of heat. Right? That's how you get that like insane 93 amp current rating. And if we look at the actual RDS on, like, this is actually not very good. 3.2 milliohms. I mean, at the time of the GTX 580, this would have actually been good. You wouldn't really see many. Actually, no, because you could already get like direct FETs from International Rectifier at the time, and those you could get below 2 milliohm RDS on. Yeah, so 3.2 milliohm is actually quite high. If we look at a more like reasonable current rating for like say the case temperature is 85 degrees Celsius, then it's like 59 amps maximum current rating, which is still really high actually. But for like if you have one of these MOSFETs just sitting on a test PCB with an ambient air temperature of 25 degrees, they only do so this is air temperature, right? Not MOSFET temperature, then it's a maximum current rating of like 22 amps-ish. So that's kind of the thing. is like one of the... I'm trying to find if there's anything... Nah, that's basically all I wanted to show. We're not gonna, like, I'm not gonna calculate the actual, like, efficiency of this VRM. But anyway, so that's basically the reasoning for why the VRM on this is laid out the way it is. It's like, you know, Gainward or Gainward is basically trying to get as close to that maximum current rating as possible. And the best way to do that is like lower the thermal density by spreading your heat generating components further apart, and then put a great big freaking heatsink on them, right? Because yeah, this is actually a very nice VRM heatsink. Like, I like it. So, and I find it kind of interesting that like you don't find this style of VRM layout like on very many GPUs at all. Now, one of the potential downsides to this is that you do get this massive switch node, which can lead to like more like switching noise being radiated into the environment. Because this entire like connection from the high side MOSFET to the low side MOSFETs, like the voltage on that is going up and down constantly. So that generates like EMI. So that's one of the reasons why you don't see ginormous switch nodes a lot of the time, is just keep this switch node as short as possible to minimize the amount of EMI the VRM generates. But from a like thermal management perspective, this is actually a really good idea. Another benefit to this is that if you look at the thermal pad, obviously we have a imprint of the... Actually, I'm not sure that this thermal pad even makes contact with the PCB, which is potentially a bit of a shame. But the thing is, the MOSFETs are obviously soldered to the, you know, like copper of the PCB. So the thermal transfer from the MOSFET into the PCB is actually generally better than the thermal transfer from the MOSFET into its like black casing material, because that's not metal. So the thermal resistance of that casing material is actually relatively high. And so, you know, like transferring the heat into the PCB and then out of the PCB into a heatsink is generally going to be more efficient than just trying to pull the heat directly out of the MOSFET itself. So, yeah, basically this is like a cost-effective way of getting more current handling capacity out of your VRM without having to resort to using more components, right? Like more phases, more MOSFETs, better MOSFETs, that kind of thing. Is like, nah, you just take the same MOSFETs that you always use, but you just put more space between them and potentially significantly reduce the operating temperatures by doing that. So now, annoyingly enough, I don't really see a way to test. Actually, because this is basically the same VRM as a reference GTX 580 VRM. So this shouldn't be actually, like, you could... I mean, you'd have to run a bare PCB comparison, right? You can't do a comparison where each card has a different VRM heatsink assembly. But that could be a test that I might do, is just see like how hot does this run with no heatsink versus how hot does a more compact VRM layout run. Now, obviously, there might be other differences like switching frequencies, what kind of drive voltage we're using. I don't think I see a 5-volt regulator. Oh, no, this is probably a 5-volt regulator over here. That doesn't necessarily mean that they're using it as the drive voltage. So, yeah, that I'm not like... That would need closer investigation on my part. Because depending on what voltage you use to switch your MOSFETs on and off, the resistance of them is lower or higher. So with like there's quite a few cards that'll actually just use straight 12 volts for switching the MOSFETs on and off. And in that scenario, you get significantly lower on resistance. But the downside is that with switching the MOSFETs on and off with 12 volts has more like power consumption in the like switching action itself. So if you're at low load, the VRM actually is less efficient by doing that. So that's a bit of a balancing act. And in fact, it's such a balancing act that there are some cards that'll have like a 7-volt regulator on them, where they'll take 12 volts and regulate it down to 7 volts just to drive the MOSFETs, because that gives you like a middle ground of like reduced RDS on, but not quite the high switching losses that you get with 12 volts. So, yeah. Other than that, ooh, these are Panasonic capacitors. Not something you see very often these days, but back in the day, actually quite common. like Panasonic through-hole capacitors. These days you'll see a lot of Panasonic SMD polymers, but the through-holes for whatever reason are not that popular in at least like enthusiast hardware. I don't know about like Dell HP or whatever, but yeah, like most motherboards and GPUs for their through-hole capacitors will just use Nichicon or Nippon Chemicon or APAC, which is a Taiwanese manufacturer. So yeah. Anyway, that's it. Oh, and obviously we have shunt resistors over here. Oh, wait. I'm not a fan of this like input filtering setup. I'm sure those input filtering inductors are rated for whatever current they're supposed to be handling, but it's weird seeing like this is pretty typical for filtering like 3.3 volts or something, but for 12? Well, actually, for memory power, I've seen that on a few cards as well. Oh, and we have another regulator over here. This is probably 1.8 volts for the, I'm assuming, BIOS chip. So, wait, where's the PEX rail? Now that I say that. Probably this. Yeah, that's going to be a PEX rail. So, yeah. That's the... You know, actually, I just realized this has a completely... This uses the ADP 4100, whereas, like, a regular GTX 580 uses a... Actually, I could also do a comparison against a regular GTX 480, because that's, like, the power... As long as you match the current draw, it's, you know, the VRM doesn't care what's actually on the other end of it that much, from a thermal perspective. But this is an ADP 4100, whereas the, like... reference PCB and was using a CHL 8266. So this might actually have significantly different voltage regulation behavior from the like reference design, because it is a completely different VRM controller. And again, I don't think I've ever actually measured a 500 series that had like really terrible voltage regulation. Back in the day, the GPUs just didn't have as aggressive power transients as far as I can tell. So I don't think I've measured a 500 or 400 series with more than like 200 millivolts peak to peak on the core power rail. But anyway, so yeah, and honestly, like looking at this might actually be capable of handling quite a lot of current with how it's spaced out. It does, like, I want to, yeah, so, like, this is why I have, like, why I bought the card, right, is it's just, like, I find this VRM very interesting because it's, like, this is the only, it's not the only example, but it's one of the few examples of a manufacturer, instead of just, like more phases or better MOSFETs or something like that, they're just like, no, we take the same MOSFETs that we, you know, the reference board uses, but we just put, like, space for like twice as many of them on the board, and in theory improve the current handling capacity of the board that way. So yeah, I would like to test that. I'm not sure how I'm going to test that, because it is a bit awkward with how many other differences this board has. But yeah. Oh, also it's not standard to have 4 polymers behind the core for a GTX 580. So I do wonder how that behaves as well. I think normally you get 2. Might only be 1. Or I'm misremembering something. But anyway, yeah, so hopefully you found this card somewhat interesting. I mean, obviously I mainly find the power delivery on this interesting. The heatsink is a, you know, unique heatsink design. But yeah, the main thing I was interested in is just like, how well does this actually work? And why don't we see it more often? I'm guessing if, like, maybe it doesn't work that well, and that's why we don't see it more often, or because there is a lot of cards where you'll just have, like, all of these components crammed into, like, this much space instead of this much space, and then just a bunch of empty PCB behind it, right? So, yeah. Man, they really went out of their way to lay out the board to, like, maximize that heatsink. Because, like, even where they put these capacitors, right? Like, a lot of GPUs will actually move these forward so that they get them closer to the high side MOSFETs, which for the through-hole polymers, that doesn't really matter. Um, there's not actually that much input filtering now that I talk about that. Yeah, like we have all of these unpopulated multi-layer ceramic pads on the back. And then on the front, we have like, yeah, it's really not that much for the high side multi-layer ceramics. I'm okay. I'm definitely taking the oscilloscope to this thing because this is actually I'm not sure what a GTX 480 reference PCB looks like off the top of my head, but compared to a lot of modern cards, this is very different. Actually, even compared to a lot of like slightly later cards, this is quite different. So, yeah, an interesting approach to the power delivery on this because it's like, yeah, they didn't, buy better MOSFETs. They just put more space. Did it work? I don't know. That's why I bought one. So, yeah, this video went way longer than I was planning for it to go. So hopefully you found it somewhat interesting. Yeah, thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with Actually Hardcore Overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, hoodies, posters, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. And that's it for the video. So thank you for watching and goodbye. And I need to get to the stop button.